Hello folks, I'm going to start the next one of 4.5. Second part of it is entitled Newton's Method. It does use linearization in a sense. I have a sketch here that I took from the book. Again, not the greatest sketch. The point is, if there is a function that cuts through the x-axis, I can find the x-intercept by a method of approximation answers through the idea of tangent lines or linearization. Newton's method is a type of formula that is used on your graphing calculator, in a sense, when you have to give it a left bound and a right bound and then a guess. It enables you to figure out what that is through the process that we are going to discuss. So, couple step process, nothing major. First thing we do is if we have a function, we try to pick a value that is relatively close. Now, it doesn't matter how far away you are, you would eventually get to it, but the number of what we would call iterations might be up into the 10, 20, 30, 40, depends how far you are away, and we don't necessarily want to have that much work nor that much time. That's why it's such a nice program for the calculator. It's a very simple procedure. So we start off by picking a value. Again, if you can, quick sketch a graph might help you narrow it down. Again, we could use the idea that we could trap it between two values. Maybe this one makes it positive, this one makes it negative, and then we can use the intermediate value theorem in a sense to negotiate our answer. So make a guess, and then you can use this formula, which is a form of the linearization formula. Basically says it's your first guess minus the first guess into the function, looking for the y answer, divided by the first guess into the derivative function. So in a sense, you're taking your guess and you're subtracting the y value by how it's changing, and that will give you the next guess. And you just continue to do that until a pattern begins. Now by that I mean you start to see the answers have the same decimal as you continue on. So that's the idea. So let's hop to it here. First one, an equation that is the cubic equation of x cubed plus 3x plus 1 is equal to 0. And here is my first guess. Now, I got this first guess by just logically thinking if I have this negative 1 and this is negative 3 and this is positive 1, my first answer is going to be negative 3. Now that's far away, but that's a good place to start. Here's my derivative that I have to use. Now remember, Newton's method. This is your first guess. This is your second guess that you're creating. So first guess minus the first guess into the function divided by the first guess into the derivative. Well, in the function right here, you create the value of negative 3. The value of the derivative, the slope at that point, is 6. This creates a positive 1/2. That allows my second guess to be negative 1/2, or if I list it over here, negative 0.5. Now I just repeat the process. My third guess will come from my second guess, negative 1/2, minus the second guess in the original, divided by the second guess in the derivative. That creates this crazy looking fraction, which actually turns out to be 1/6. Put these two together, I now get a third guess being negative 1/3. So you can see it's changed radically from here to negative 0.5 to negative 0.3, repeating. Now I can tell my guesses are getting closer because my movement isn't as rapid. If this went from negative 1 to negative 10 to negative 12, I still have a little bit to go, but you can see it's beginning to get closer. Okay, repeat the process. Put the third guess to create the fourth guess in, third guess in the original, third guess in the derivative, creates this, which makes the fraction of negative 29/90. Now, of course, we would have a hard time figuring out approximately what this is because the repetition, we'd have to figure out a common denominator. That's one of the nice things that we can quickly change to a fraction on our calculator. It's not a method we're going to use too often. We have other techniques, but this is one technique that can exist, but we would never use it for a practical standpoint. Now you can see I'm at 0.3 with repeating 2's, so the area has gotten smaller. So I will do a fifth guess, taking my fourth guess in the function, divided by fourth guess in the derivative. Really messy looking fraction. Gives me this massive answer. Well, that turns out to be this. So now you can see the 3's are the same, the 2's are the same, The 2's are the same because that repeats, and now I'm at 1. So I am now within basically 4 decimal places, which is pretty good. The true answer, in effect, if I solve this through either graphing it and using my grapher to figure out the answer, or if I have a T89, I can solve it. Here's the correct answer I'm looking for, and here's what 5 guesses have gotten me. You can see I'm already at 1, 2, 3, 4, 5, 6, 7, 8 decimals correct to the true answer. And that's not bad after 5 guesses. That's what Newton's method does. It's a series in the sense of linearizations to allow me to find the values as it gets closer. This is not part of our AP test for AB. It is an a BC test. It probably comes up in terms of a multiple choice. And it is also used with something we call differentiables. Now, differentiables is errors that how far we are off. We are not going to use that in this semester. We will talk about it next year if we take BC. But really, I just want to introduce Newton's method as it is seen. We'll look at another example here. Now, this example isn't Newton's method. This example is a quick review, which I think we need to do, about a problem that has vertical asymptote behavior, but would allow us, again, to do everything we've done in Chapter 4. So this has nothing to do with Newton's method, nothing to do with linearization. It's just a whole Chapter 4 process problem. And it's a neat problem, so I want to throw it up. So here's your basic rational function. Typically in pre-calc, algebra 2, you set it equal to 0 and you solved it. And we had the good zeros on top, which were our x-intercepts. The bottom gave us our vertical asymptotic behavior. First derivative is what we did. This tells us the increasing and decreasing of the function. So, found my first derivative, set it equal to 0. There's my good 0. And there are my bad zeros. Notice the square that has to come back into play here because in my plus minus chart for increasing, decreasing, there's the 0, but these two show up twice because of it being squared. The factor of these two multiply, make a full x squared minus 2. I need to square that. Kids sometimes miss that. Notice my function is decreasing, and then it is increasing. So here's all my critical points. Now we go ahead to second derivative for concavity. Again, using the quotient rule from this value, gives me this function. Set it equal to 0. Good zeros, there aren't any. If I divide by -4 and begin to solve this, I get imaginary solution. No zeros from the numerator. Denominator, of course, same zeros, which makes sense because remember, once it's bad in the first derivative, it's not going to become better in the second derivative. Set up my plus minus chart using all my factors. The -4, the 3x squared plus 2, and notice these are now cubed because that breaks apart into 2 separate cubes. Concave down, concave up, concave down. In a sense, these could be possible inflection points, but you're going to see they're not going to be points of the graph because these are your original your original vertical asymptotic behavior that we have going on. So let us take this page of x and y intercepts along with the vertical asymptotic behavior, along with decreasing, increasing, and along with the plus minus chart for concavity. Let's slide this one over a bit. Let's create this one over here. Let me go ahead and reduce that a little bit so we can see it. Okay, so I have here some x-intercepts at 0. There it is. Okay, whoops, I'm off one derivative. Apologize. Go up a little higher. There we go. X-intercepts at positive and -2, and there they are. Okay, and vertical asymptotic behavior at square root of 2 and negative square root of 2. Now, what I can do is if I wanted to, I could go ahead and find the y-intercept. Very simple. Let 0 happen in this equation, and you get positive 2. Now I move to my first derivative. It is decreasing before the square root of with the negative. It is decreasing before 0. It is increasing after 0. And it is increasing after the square root of 2. Now what I'm going to do with this particular function is I'm going to create the next value using the concavity. Okay, and with the concavity, I have to use this chart here. You can see before the vertical asymptote, it's concave down. Then it is concave up between these two values, and it is concave down. So, with this negative slope here, concave down. Between these two, concave up, and then concave down. This is how we can take a single function, as we have illustrated here, rational function, find your zeros, find your vertical asymptotic behavior, create your increasing decreasing to get your brief sketch of the slopes, and then bringing in the concavity from there. Any questions, please don't be afraid to ask, and I will assign the homework problem next time we meet. Thank you.